Welcome to this ninth lesson about evolution and reinforcement learning. So far, we have seen that we could combine reinforcement learning to find more optimal policies or more optimal actions or to favor diversity. Here we will see that we can evolve different things. So what else can we evolve? For instance, we can evolve the environment. This gives rise to the POET and many other algorithms where the environment is becoming increasingly complex so that the reinforcement learning agent performs some kind of automatic curriculum towards more and more difficult capabilities. So this is this paper. I won't cover this topic, but there would be some lessons to do about this. You can also evolve the agent's body. Actually, the body is part of the environment. So from the perspective of the agent, what you have to control is the environment through somebody. And here you have a picture showing that you can change the body of your agent in the environment. So that's the case of this algorithms and many others that are cited here. Or you can, for instance, evolve the hyperparameters of the algorithm itself. And that's population-based training, and this is what we will focus on during this lesson. So let's introduce population-based training, first by saying that hyperparameter search is crucial in deep reinforcement learning. If you have played with deep reinforcement learning algorithms already, you have probably spotted that it was difficult to tune the hyperparameter so that you get something that works. And population-based training will be a solution to this hyperparameter search. Actually, population-based training has been used in particular by Google DeepMind and maybe OpenAI in several notorious applications of deep reinforcement learning, such as the case where reinforcement learning agent learned to defeat strong players in the StarCraft games, or in this paper where they are trying to show that having a large diversity of environment and tasks makes an agent that is capable to generalize to other tasks. So in the rest of this lesson, we will consider the evolution of hyperparameters and policy parameters, and we will note H, the hyperparameter vector, and theta, the parameter vector. So what's the general idea? You can recognize the same drawing as before, but now we have a population of agents which have in yellow hyperparameters and in blue parameters of the corresponding neural network, and you are just using the combination of evolution and reinforcement learning to evolve these agents, so both their hyperparameters and their parameters. So if you have a population of agents, by performing evolutionary selection and variation on these agents, you also perform evolutionary selection and variations on their hyperparameters. So you will select combinations of hyperparameters and neural networks that perform well, which is a way to select well-performing hyperparameters in a population of agents. And what is very specific in this approach to hyperparameter tuning with respect to standard methods where you first fix the hyperparameters and then you learn your agent is that here the hyperparameters are evolving along training. So you can have different hyperparameters in the beginning of training and in the end of training, which makes sense because it may be the case that in the beginning of training you need a lot of exploration, and in the end of training you need very few exploration, and that you have some exploration rate that evolves through time, for instance. We will see that this population-based training architecture and algorithm is quite simple, and in particular that the variation selection operators, which are explored and exploited here, could be much improved by using more advanced knowledge in the evolutionary computation domain. So to focus on these exploration and exploitation operators, there are two explore strategies. One is called perturb, where each hyperparameter is randomly perturbed by a multiplicative factor between 0.8 and 1.2, and each parameter is perturbed independently. And the other explore strategies consist in resampling. So you have a prior distribution of hyperparameters, and each time you want to change a hyperparameter, you resample it from the original prior. In the paper, the authors seem to only use perturb, so we don't know about the performance of the resampling strategy. Besides, they have two exploitation strategies. One is called t-test selection, It consists in uniformly sampling another agent that replaces the current agent if its last 10 episodic rewards are better than the previous agent using a Welch t-test. So it makes sense. It means that if your agent is significantly better than the previous one, then it should replace the previous one. And the other one is called truncation selection. So here you rank all agents, and if the current agent is in the bottom K%, you replace it by one which is in the top K%. So you remove bad agents, you reproduce good agents, which is quite standard in evolutionary methods. But this is done in a rather naive way. And now, if you look at how the algorithm behaves, you can see here that through time, every hyperparameter changes. So for instance, here you have an entropy cost in a soft actor critique, for instance, algorithm. And you can see that in the beginning, the entropy cost is between -3 and -4, but through time, the solutions where the entropy cost is closer to -3.5 disappear, and you only get an entropy cost between around -3.8. The same with an intrinsic reward cost, or with the learning rate. You can see, for instance, here that the learning rate is getting more and more negative through time along the evolution, which means that agents that had a less negative learning rate disappeared through evolution and were replaced by agents which had a larger negative learning rate. You can also see through these diagrams that most hyperparameters do not converge to a single value. You always have some diversity in hyperparameters into your population. So in the paper, they study different properties of the algorithm, and one is the effect of the population size. Here you have the performance of agents in Atari games, and you can see that with a population of 10, the performance is similar to the performance of an agent which is not using population-based training. You would have a rate of 1 if it was exactly the same. But when your population size grows, your performance gets better and better. Actually, there is a small methodological issue in what they are doing here, because if they have more agents in the population, it means more samples, so it's normal that you get a better performance. So yeah, they should compare with a larger population, but with a constant budget, so removing some trajectories when there are more agents. Another thing that they investigate is the effect of the evolution of hyperparameters. So here they measure the performance with fixed final hyperparameters. So they evolve the population that get some final hyperparameters values, and then they perform reinforcement learning with these fixed hyperparameters values, and you can see that the performance is much lower, which means that having parameters that evolve through time is highly beneficial to the performance. Together with some students, we studied the effect of the population size on a small concrete example. So here, this is a benchmark which is called Pendulum. That's a very simple one-dimensional problem. And we went to the idea that with small populations, we got quite poor performance. And this is only with a population of 100 agents that the algorithm could find a solution that performs well on Pendulum, which is a little disappointing. And which shows that if you want to use population-based training, first, the architecture is a little complex, but also you need large computational resources. This is why those algorithms were used in very large experiments such as StarCraft or OpenAI, open-ended learning study. But probably less people use them for standard reinforcement learning experiments because it's too costly. Finally, as I said, the evolutionary part is quite naive, and it could probably be much improved. So it would be interesting to investigate whether it is possible to get population-based training that works with much smaller populations with more powerful evolutionary parts. And that's it for that lesson, and thank you for listening.